Yes, a direct current 750 volt, 1500 amp feeder can be run in 3 separate steel conduits and connected in parallel. Article 300.3 C. 2 of the National Electrical Code permits the use of steel conduits with direct current circuits, provided that the conduit is grounded. Article 392.11 requires that conductors and multiple conduits be paralleled only if they are of the same length and have the same impedance. For a 1500 amp direct current feeder, the minimum conduit size would be 6 inches in diameter. Dividing the total current, 1500 amps, by 3 conduits results in 500 amps per conduit. Using a 6-inch conduit with 3 conductors, the maximum allowable ampacity for each conductor is approximately 480 amps. Direct current tends to concentrate near the surface of a conductor, known as the skin effect. This can cause uneven current distribution in parallel conductors. However, for larger conductors like those used in this application, the skin effect is minimal and typically not a concern. Direct current creates significant magnetic fields around conductors. Running the conductors in separate conduits helps to reduce the overall magnetic field strength. Steel conduits can provide a path for stray current, which can lead to corrosion and other problems. Proper grounding is essential to minimize stray current. The steel conduit should be bonded at all joints and terminations to ensure continuity of the grounding path. Insulated conductors should be used within the conduits to prevent arcing and short circuits. Running a 750 volt, 1500 amp direct current feeder in 3 separate steel conduits is permitted by the NEC, provided that the conduits are properly sized, grounded, and bonded. The use of multiple conduits helps to reduce magnetic field and skin effect issues. When installing a high current direct current system, several factors must be carefully considered to ensure safety and compliance with electrical codes. Firstly, understanding the National Electrical Code, or NEC, requirements is crucial. The NEC provides specific guidelines for direct current systems, including conductor sizing, overcurrent protection, and grounding. It's essential to consult the latest edition of the NEC and any applicable local codes before starting any installation. Secondly, conductor selection is a critical aspect. The conductors must be sized appropriately to handle the 1500 amp current. Factors to consider include the ampacity of the conductor, which is the maximum current it can carry continuously without exceeding its temperature rating, the ambient temperature, which affects the conductor's ampacity, the type of insulation, which also affects the conductor's ampacity, and the derating factors for multiple conductors in a raceway. Copper or aluminum conductors can be used, but copper is generally preferred for its higher conductivity and lower resistance. Thirdly, conduit selection and installation are vital for protecting the conductors and providing a safe and reliable system. Steel conduit, either rigid metal conduit or intermediate metal conduit, is a common choice for high current applications due to its strength and durability. The conduit must be sized appropriately to accommodate the conductors and provide adequate space for heat dissipation. The NEC specifies the maximum number of conductors allowed in a conduit based on the conduit size and the conductor's dimensions. The conduit must be properly installed and supported to prevent damage and ensure a secure connection. Fourthly, grounding is essential for direct current systems to protect against electrical shock and prevent equipment damage. The grounding system must be designed to provide a low impedance path for fault currents to flow back to the source. This helps to quickly trip over current protection devices, such as circuit breakers or fuses, and to energize the circuit. The NEC provides specific requirements for grounding direct current systems, including the size and type of grounding conductors and the location of grounding electrodes. Fifthly, overcurrent protection is necessary to protect the conductors and equipment from overloads and short circuits. Overcurrent protection devices, such as circuit breakers or fuses, must be selected and sized appropriately to interrupt the current flow before it reaches a level that could cause damage. The NEC provides guidelines for selecting and sizing overcurrent protection devices based on the conductor's ampacity and the equipment's rating. Sixthly, bonding is crucial for ensuring a low impedance path for fault currents to flow back to the source. Bonding involves connecting all metal parts of the electrical system together, including the conduit, enclosures, and the equipment frames. This helps to equalize the potential between different parts of the system and prevent electrical shock. The NEC provides specific requirements for bonding direct current systems, including the size and type of bonding conductors and the location of bonding connections. Seventhly, insulation is necessary to prevent arcing and short circuits. The conductors must be properly insulated to prevent them from coming into contact with each other or with grounded metal parts. The insulation must be rated for the voltage and temperature of the system. The NEC provides specific requirements for insulation of conductors in direct current systems. Eighthly, magnetic field considerations are important for high current direct current systems. Direct current flowing through a conductor creates a magnetic field around the conductor. This magnetic field can induce currents in nearby metal objects, which can cause heating and other problems. To minimize magnetic field effects, it is important to use shielded conductors or to separate the conductors from other metal objects. Ninthly, skin effect is a phenomenon that occurs in alternating current systems, where the current tends to flow near the surface of the conductor. However, skin effect is generally not a concern in direct current systems because the current flows uniformly throughout the conductor. Tenthly, stray current can cause corrosion and other problems. Stray current is current that flows through unintended paths, such as the earth or metal structures. To minimize stray current, it is important to properly ground and bond the direct current system. In summary, running a 750 volt, 1500 amp direct current feeder in 3 separate steel conduits requires careful consideration of several factors, including NEC requirements, conductor selection, conduit selection and installation, grounding, overcurrent protection, bonding, insulation, magnetic field considerations, skin effect, and stray current. By following these guidelines, you can ensure a safe and reliable direct current system. Additional considerations include ensuring proper ventilation to prevent overheating of conductors within the conduit, especially with high current applications. Also, regularly inspect the installation for any signs of wear, corrosion, or damage to the conduit, conductors, and connections. Implement a maintenance schedule that includes periodic tightening of connections, checking for proper grounding and bonding, and testing the insulation resistance of the conductors. Document all aspects of the installation, including conductor sizes, conduit types, grounding and bonding methods, and overcurrent protection device ratings. This documentation will be helpful for future maintenance and troubleshooting. Ensure that all personnel working on the direct current system are properly trained and qualified to handle high voltage and high current equipment. Follow all safety procedures and use appropriate personal protective equipment such as insulated gloves, safety glasses, and arc flash protection. Consider the potential for harmonic distortion in the direct current system, especially if it is connected to a power electronic converter. Harmonic distortion can cause overheating of conductors and equipment, as well as interference with other electronic devices. Use appropriate filters or other mitigation techniques to reduce harmonic distortion. Investigate the possibility of using alternative conduit materials such as aluminum or fiberglass, which may offer advantages in terms of weight, corrosion resistance, or cost. However, ensure that the chosen conduit material meets all applicable NEC requirements and is suitable for the specific application. Explore the use of active harmonic filters to further mitigate the effects of harmonic distortion. Active harmonic filters inject compensating currents into the system to cancel out harmonic currents, resulting in improved power quality and reduced equipment stress. Evaluate the use of smart grid technologies to monitor and control the direct current system. Smart grid technologies can provide real-time data on system performance, allowing for proactive maintenance and optimization of energy usage. Develop a comprehensive emergency response plan to address potential incidents such as short circuits, overloads, or equipment failures. The emergency response plan should include procedures for isolating the direct current system, shutting down power, and evacuating personnel if necessary. Consider the impact of the direct current system on the surrounding environment. Minimize noise pollution, electromagnetic interference, and other potential environmental impacts. Use environmentally friendly materials and practices whenever possible. Consult with qualified electrical engineers and contractors with experience in direct current systems to ensure that the installation is properly designed and installed. Their expertise can help to identify potential problems and ensure compliance with all applicable codes and standards. Implement a robust cybersecurity strategy to protect the direct current system from cyber attacks. Cybersecurity threats can compromise the safety and reliability of the system, as well as potentially disrupt power supply. Consider the use of surge protection devices to protect the direct current system from voltage surges caused by lightning strikes or other events. Surge protection devices can help to prevent damage to equipment and improve system reliability. Furthermore, conduct regular training sessions for personnel working on a direct current system to reinforce safety procedures and ensure that they are up to date on the latest technologies and best practices. Training should cover topics such as hazard awareness, lockout-tagout procedures, and the proper use of personal protective equipment. In addition to following NEC requirements, consider adopting industry best practices for direct current system design and installation. These best practices can help to improve system performance, reliability, and safety. One such practice is to use redundant components in critical systems to ensure that the system can continue to operate even if one component fails. Redundancy can be implemented in various ways, such as using multiple power supplies, parallel conductors, or backup control systems. Another best practice is to use advanced monitoring and diagnostic tools to track system performance and identify potential problems before they lead to equipment failures. These tools can provide real-time data on voltage, current, temperature, and other critical parameters, allowing for proactive maintenance and troubleshooting. To further enhance safety, consider implementing arc flash protection measures in the direct current system. Arc flash is a dangerous phenomenon that can occur when a short circuit or other electrical fault causes a sudden release of energy in the form of an arc. Arc flash can cause severe burns, blindness, and even death. Arc flash protection measures include using arc-resistant equipment, installing arc flash relays, and providing personnel with appropriate personal protective equipment. When selecting equipment for the direct current system, choose components that are specifically designed and rated for direct current applications. Using alternating current rated equipment in a direct current system can lead to premature failure or even hazardous conditions. Also, consider the long-term reliability and maintainability of the equipment. Choose components that are known for their durability and ease of maintenance. In addition to electrical safety, consider other safety aspects of the direct current system, such as fire safety. Use fire-resistant materials and construction techniques to minimize the risk of fire. Install fire detection and suppression systems in areas where there is a high risk of fire. Finally, stay up to date on the latest developments in direct current technology. Direct current technology is constantly evolving, with new products and techniques being developed all the time. By staying informed, you can ensure that your direct current system is using the most advanced and efficient technologies available. Remember that careful planning, design, installation, and maintenance are essential for ensuring the safety and reliability of a 750 volt, 1500 amp direct current feeder system.